In this lesson, we're going to take a look at using density curves. We're also going to look at the 68, 95, 99.7 rule. We're also going to take a look at using z-scores. But before we get started, let's do a quick recap of the shape of a distribution and five-number summary and mean and standard deviation. So you'll see we're starting with the New York Knicks roster, and there's some really nice quantitative data that we're going to look at using this current Knicks roster today. But before we do that, I'm going to jump back, just do a quick little sketch, quick little demo of the three basic shapes of distributions that we're going to discuss, at least in this introductory statistics course. So as we mentioned last time, you have what's called a skewed left distribution. And if we looked at what a skewed left distribution would look like, if this is your axis, say we're going from the values of 0 to 100, you're going to have most of your values actually towards the high end. So when I draw these distributions, I make my taller bars over here. Maybe you have some uniform intervals, but for the most part, as you get down to the lower end, it starts to tail off. So it might look something like this. You might even have a gap. But if I were to trace a curve over this, I kind of see a hill going from right to left. Okay. If I have a skewed left distribution, I want to use the five-number summary, which is the minimum, the first quartile. I also want to take a look at the median, or the number that is in the direct middle of the observation, the third quartile, and also the maximum. I want to refrain from using the mean and the standard deviation, and we'll explain why in a second. Now, these five numbers, this five-number summary, I'm also going to use it in a skewed right distribution. And a skewed right is the opposite of skewed left. It's like taking this and just flipping it. If we were to take it and flip it to the right, once again going from 0 to 100, and I'm going to try and mirror this type of distribution almost the same exact way, where you have a couple outliers over here. And once again, if I were to draw or trace from left to right, I would see the hill kind of tapering off, or the tail tapering off to the right. In this case, I still want to use these same measures, right? I want to use the minimum, the median, the maximum, and then the quartiles over here as well. Okay, I'm not going to rewrite them. I'm just going to have that nice little circle represent these guys going over here. So to predict values, let's just say for this case, I wanted to say, all right, what percentage of the values fall beneath, say, 40? Okay, I can just look visually here and see, okay, maybe 60 to 70%. Most of my distribution is below 40. But to get a better idea of what that number would take on, I would look at these five numbers. Now, what about if we have a distribution that's a little more consistent? Okay, and that's what we're going to look at mostly today, and that's our symmetric, or sometimes called our normal distribution. Okay, and think about visually, it would be like taking these two distributions and just like scooting this one over a little bit, scooting this one over a little bit, and you would see it would form a nice bell-shaped curve. All right, and just to kind of redraw it, we're going from 0 to 100, and I have outliers, and as I work my way in to the middle, I see the bulk of my data towards the middle. And if I were to draw a curve over top of it, it would look like a bell. All right, it would look like a nice hill. It's very symmetrical. In this type of distribution, I don't want to use the five-number summary. I want to use the mean and the standard deviation. Okay, and standard deviation is a way to measure the spread. It's sometimes referred to as S, as sigma. All right, for the time being, for this introductory stat course, I just want you thinking about the standard deviation as a way to measure how spread out the values are. Okay, so if the higher my standard deviation is, the more spread out I have my values. So if I were to go to a sporting event and measure the ages of the players on the team, okay, the standard deviation for that distribution is probably going to be much, much lower than the standard deviation of, let's say, all the spectators in the game. Okay, I could have spectators ranging from age 5 all the way up to 95, whereas for the team, we're probably in a 10 to 15 year range from say 21 until 35. Okay, so the lower the standard deviation, the lower your spread is. But let's get back to why I would want to use just the mean and the standard deviation. And the analogy or the comparison that I always think of in my head is given these three histograms, which one would you say is the most consistent or the most predictable? Okay. And I think we can all agree that just based on the way this thing looks, I would go with our skewed distribution being the most predictable. If I asked you the question, what percentage of our scores are beneath the age of 40 or beneath this number of 40, I can use my mean and my standard deviation to get to that number. It's much more predictable. It's much more consistent. This is a little more erratic, and this is once again, a little more erratic. So for something that's more consistent, I don't need 5 numbers to measure percentages. I only need 2, okay, because it's more consistent. You can always go back to over here, we're using 5 numbers. Over here, we're only using 2, okay? These guys over here, think of it as if we were a supervisor, right? These workers over here are less consistent. Sometimes they show up to work, sometimes they don't, sometimes they have great days, sometimes they don't, all right? As a supervisor, I need to check in on them more often, right? I need to see, hey, are they showing up to work? Are they doing the right thing? Are they giving good customer service, right? I have 5 checkpoints for that, all right? My symmetric, my normal, my good looking, my prepared, I'm predictable. He's my worker she's always on time. She's always working hard. She greets people with a smile. I know she's going to do her thing. I only need to check in on her twice, okay, to evaluate her performance. All right, that's how I remember to use just the mean and the standard deviation for a symmetric or a normal distribution. So what that means for us today, during this lesson, every distribution we're going to look at is symmetric, or we're going to assume that it's symmetric. We're going to assume it has a normal shape. All right, to use the 68, 95, 99.7 rule, and to use z-scores, and I'm just going to write up here those 2 rules. So to use 68, 95, 99.7, and also z-scores, the prerequisite, the requirement, is it has to be symmetric. These 2 rules are great to use, but they only apply to symmetric situations. All right, they're only over here. You really can't use them over here. They wouldn't apply.